Hi folks, welcome to another set of ICP video notes. Today we're going to learn about heat and work. So as you know, the total amount of energy never changes in a closed system. In fact, the energy can transfer between kinetic and potential energy, but when you add those two up, the total energy is always going to be the same. It's really nice when we can do all of our math inside of a closed system, but that's rarely how it actually works in real life. As you know from experience, a bouncy ball that's dropped on the ground never quite bounces back up to where you dropped it from. It loses energy each time it hits the ground. This is what we call an open system. In an open system, we can lose energy. To be clear, that doesn't mean the energy just disappears. It leaves the system that we're in, but it gets transferred into another system. For instance, each time the ball hits the ground, it makes a noise. It takes energy to create that noise. There's two basic ways to lose energy from a system. You could lose energy through heat or through work. Heat is a transfer of thermal energy. So for example, when you place an ice cube in a glass of warm water, the warm water transfers some of its thermal energy into the ice. When the warm water loses thermal energy, it cools down. And when the ice gains thermal energy, it melts. The equation for thermal energy is Q equals mc delta T. Q is the heat quotient, or the amount of thermal energy that gets transferred. M is the mass measured in grams. C is the specific heat, which you'll always be given. That's how much energy it takes to warm up 1 gram of a substance by 1 degree Celsius. And finally, delta T is the change in temperature, which you can find by subtracting final temperature minus initial temperature. You can manipulate this equation in all sorts of ways to find the mass, specific heat, or temperature change of an object. We do still have the larger law of conservation of energy, which says that we cannot create nor destroy energy. So, if thermal energy is added to one object, the same amount has to be subtracted from another. So let's go to the board and practice the basic form of this equation. Okay, so our heat problem asks how much energy is transferred or released through heat when 30 grams of water, starting at 96 degrees Celsius, cools down to 25 degrees Celsius. And then it tells us that our specific heat of water is 4.184 joules per gram degree Celsius. So we write down first our equation, then we write down what we know. We know the mass is 30 grams. The specific heat is 4.184 joules per gram degree Celsius. The final temperature, that's the temperature it ended up as, is 25 degrees Celsius. The initial temperature was 96 degrees Celsius. And the change in temperature we find by taking the final minus the initial. So we just plug all of this into our equation. We get that the heat is equal to 30 grams times 4.184 joules per gram degree Celsius times, in parentheses, our final degree minus our initial degree. When you do that, the delta T then will equal negative 71 degrees Celsius. That negative is super duper important because that tells us that the water lost energy. So when we multiply all three of these together, we get that the heat is negative 8,911.9 joules. And again, the negative meaning that the water lost that much energy. We could do a problem where we go through all of this, we find out the water lost that much energy. That means that all of that energy went into the ice that you put in the water to cool it down. So then we know that the ice's heat quotient is 8,911.9 joules, which means that it gained that much energy, and you could plug it back into one of our equations to find the mass of the ice. But we're not going to do an example of that just yet. The second way we can lose energy from a system is through work. When you push a chair across the classroom, you perform work. You provide that chair with energy to move across the classroom. The chair gains energy from you. That's what makes it move. It has now kinetic energy. And since the chair is gaining energy from you, you are losing that energy. The equation for work is W equals FD, where W is the amount of energy that's transferred through work, F is the force applied to the object, measured in newtons, and D is the distance the object moved, measured in meters. You can manipulate this equation to also find the force applied or the distance moved. So let's practice the basic form of this equation. Our work question asks how much energy or how much work is required to pull a sled 5 meters if you're putting 60 newtons of force on it. So again, we write down our equation first. This one, in my opinion, is a lot easier. There's less variables and there are things that should make sense to you by now. The force is 60 newtons, according to our problem. The distance is 5 meters. So we just plug that in. The work then equals 60 newtons times 5 meters. And you get that to be about 300 joules. So you have to put 300 joules worth of work into pulling that sled that distance if you're only putting that much force on it. Well, that's all for our notes video today. I hope that you were able to learn a bit about heat and work and the math that goes into calculating how much energy gets transferred from one system to another.